Okay, do you have any questions for me?
I don't think so.
Okay. Let me pull out some problems. I think we have someone joining us, so we'll see if they have any questions before we move on. Hi, Alice. Do you have any questions for me? Can't hear a thing. I can see you laughing, but
Sorry. So did you cover the science lab
no,
that,
that was
and
just
is it,
where you read it and you submit your answer to the website. You actually type it in. You don't type it in. You don't put it in
an
your
essay?
Yeah.
Okay. Yeah,
So
I
it's
just
pretty-
kind of discovered it a second time, and then I was like, wait a minute, was there any discussion about this that I missed?
Nope,
So,
it's pretty open.
okay. Okay.
So those are clearly I'm concerned about people not understanding how science is done and therefore not trusting science. And so I kind of want you to summarize those articles and why people should trust the science. Maybe not trust an individual scientist, but trust the science, because we have mechanisms in place to check on people who falsely represent science. Whereas,
Mhm.
in many other venues, you don't have anyone checking on whether or not that person is uh, trustworthy. So a lot of these news programs, which aren't news programs, they're really commentator programs. And you hear those
Mhm.
commentations where they say this and this and this and blah, blah, blah. Can you really trust them when they don't have any sort of vetting? They don't have anyone checking on them. They don't have any, you can't. So that's why, I'm
So
I'm gonna say that's
do
why I'm
you
hesitant to
mind
look
if
at
we,
Fox and them, Fox, CNN, all of that.
yeah,
But science,
right.
on the other hand,
So
Fauci,
do you mind if in our essay we represent kind of an awareness?
an awareness of, was there a last part to that?
Sorry, my internet is a little iffy right now. Could you say that again?
An awareness of, you said awareness, and then that was it. That's what I heard.
Do you mind if we speak of an awareness of the bias that's put out on social media, like the very first results of a first study being part of why people don't trust it because it's then disproven later
I could,
by
I
another
could,
study?
you could put as that as part of it, but you also might put out there why we should really trust the science. That's the focus, not why we just trust other things, but why we trust the science. Something that should be taught in high school. In high school, they teach the scientific method, but they don't really talk about how science is done and how it's vetted. And I think that's important. And so that's why I had you read those particular sections, because it's about how science is done and how it's vetted with your colleagues. All right. So yeah, there's nothing to, there was no discussion there. Although it could be an interesting discussion. All right.
Well, I think it would help people understand the conflict between people who don't trust and people who do. Just less of a division.
I think it's
But,
evident in the reading.
Yeah.
It's obvious people don't trust scientists because they say, well, scientists are humans, they could lie. Furthermore, scientists are humans, so they might espouse their own personal view. And furthermore, they might say, well, you can make science say anything, and so forth and so on. So these are very, what I would consider uninformed views based on the reading. So I think, this should be mandatory reading for all high school students. Then you might have people saying, okay, so that person who says it's ancient aliens, how many people have vetted his ideas? You know what I mean? And you're going to find out, well, very few, because you just can't do research in that area. You can't come up with a hypothesis that there's ancient aliens and prove it. So that's another pet peeve of mine, is ancient aliens. If you can't explain anything, it must be ancient aliens. That's the only alternative. The alternative can't be, well, we don't understand it yet. It's ancient aliens. I'm an ancient alien. I'm just kidding. But I am made out of stars, so that I'm not kidding about. You've all heard that Moby song, right? We're all made out of stars. So, does that make me an alien, since the matter I came from a different place? I guess so. Does it make me ancient? I guess so. We're all ancient aliens. And one of you I know is a musician. I know you're a musician. And you can write a beautiful song, maybe rock and roll song, about how we're all ancient aliens. So the History Channel is in fact true. We're all ancient aliens. Okay, so that's my little digression for the day. Let's go ahead and do some problems from the back of the book so that you can prepare for the exam, which we're going to have next Thursday. When I say next, I don't mean tomorrow, I mean the following Thursday. So my next refers to like next week, not this week. So we're going to have an exam next Thursday. So that's a week and a day from today, over chapters 1 and 2. I'm not going to give you the test on Friday, because Friday is actually a holiday. I think it's Veterans Day. So I'm not going to assign any work on that day. Or President's Day. Maybe it's President's Day. And then the following Monday is like Lincoln's birthday or something like that. I don't know why they have President's Day and then Lincoln's birthday, but they have like 2 separate days. So there'll be a period there where, I'll give you stuff to look at, but I won't count those days as work days. Okay. So we're in the midst of chapter 2, and I'm looking at the questions from the back of the textbook, and there's like 168 questions. And so we'd like to get through the rest of these by Monday, so that on Wednesday we're on to chapter 3. Okay. I don't like to finish up chapter 2 on Wednesday and say, okay, here's your test the next day. All right, so I'm going to change my share to my trusted Elmo. Okay, so there's the Elmo. Let me adjust things there. Okay. And here we can see some of the questions that we've already done. Mass number, gold atom, atomic number, and mass number. So these things are in previous Q&As. That's why I'm kind of glossing over them. Number 8 was one where we're supposed to give the number of protons, neutrons, and electrons in technetium and another element, I can't remember which. Number 10 is actually a problem, I believe, that is in your homework. We talked about John Dalton's model, but we also talked about Rutherford's model and what he found out. And I believe we did this one too, the mass of one oxygen atom in grams. And for that, we need to know that 1 AMU is 1.66054 times 10 to the minus 28 grams. I believe we did this one too, where I showed you how to calculate molecular weight. And we had set this one up, but I didn't do the work. Well, no, I'm sorry, not this one. This one was very, very easy. The first, second, and last one are isotopes of element X, because when you write the standard symbol of an isotope, the number on top is always equal to or greater than the number below, not the other way around. This does not exist. This says you have 18 protons, but you only have 9 things in the nucleus, and that's impossible. This is the one where we kind of looked at it and we decided that 88 is probably the most dominant of all of these, the most abundant, because the atomic weight is closest to that. And this is one where we calculated the atomic weight of magnesium. I showed you how to do that. And this is the one where we set it up where we use that formula X plus 1 along with the atomic weight formula. So we're going to move on to nothing. So we'll see you later. I hope you enjoyed today's Q&A. Okay, I actually have quite a few right here. So let's take a look at this problem here. And I'm going to explain some things to you. And usually when I explain these problems to you, I kind of make the assumption that maybe you don't know much about the problem. So it's kind of like you might feel like I'm treating you like you're really not prepared, but I'm just trying to cover the bases, okay? All right. So it says in groups 4A through 6A, there are several elements whose symbols begin with S. Name these elements. For each one, give its symbol, atomic number, group number, period, etc. So what I'm going to do here is I'm going to draw a periodic table. And I'm not trying to draw it precisely, just kind of what it looks like. So it looks like this. I call this a tower. I call this a tower. And I call this the castle wall. So this is where you patrol looking for enemies attacking your castle. Here's the wall. And I call this the moat. So you might hear me saying, oh, if you look at the tower, blah, blah, blah. Now, for this, we actually label the towers as group 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. And you want to memorize those groups. So 8A is all of these elements in this column. So groups are columns. And we all know columns are vertical, except for in Rome, they have some columns that fell down and they never made them vertical again. And then they put up a little ticket booth and make you pay to see the fallen down column. Can you imagine if the Lincoln Monument fell down or the Washington Monument fell down? We'd put it back up. I'm just saying. Maybe there was a little conflict at the time. But does everyone understand this idea of group, 1A, 2A, all the way to 8A? Now, I'm not going to bother telling you the numbers of these groups, but these are the B groups. And you might think it's, well, 1B, 2B, 3B. It's not. It's actually 3B, 4B, 5B, 6B, 7B, 8B, 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 9B, 8B, 1B, 2B. It's all numbered weirdly. These are not groups here down below. And in fact, this periodic table, if we drew it correctly, it would look more like this. So this is a smaller version. And this is called an expanded periodic table, where you can see, hopefully, that I have taken this moat, which I'm going to code with these stripes, and put it right here. So that moat is no longer there at the bottom. It's put where it belongs, which is inside of here. It's actually part of the wall. Now you might ask, well, why don't we draw the periodic table like that all the time? And the answer is really simple. If you think about an 8.5 by 11 sheet of paper, you see how the periodic table fits that really nice? But if you draw 8.5 by 11 sheet of paper here, do you see how you're left with a whole lot of space unused? So that's probably the major reason why you have a moat rather than sticking it into the wall. Okay. Now, I used to tell my students this story because I thought, well, I don't know, so I'll just invent something. So I decided I'd go look up the reason why we draw the moat down here instead of in the wall. And the answer is, turns out this fits on an 8.5 by 11 sheet of paper better than this. I was right. And that kind of reinforces the idea of Occam's razor, where usually the simplest explanation is probably correct. We don't need to invent, well, ancient space aliens want it this way and not this way, because that's a little convoluted. Who's going to believe that? You might as well say my cat likes it this way rather than that way. And that's why we've done this. And my cat is reincarnated millions of times. So that's why my cat is the reincarnation of the cat who wanted it this way. Oh, okay. So now we know about groups 4A through 6A. So I'm going to bring my periodic table here. I've got a small one here, but I'm going to zoom in on it. So here, let me focus on it also. You can actually see the Roman numeral 4 there, 4A, 5A, and 6A. So they're the ones with carbon, nitrogen, and oxygen in there. And we want to look at all of the elements in 4A, 5A, and 6A, give their symbol, atomic number, group number, period, and assign each as a metal, metalloid, or non-metal. So there's a little bit more I have to teach you about the periodic table, okay? So I'm gonna zoom back out. And we're going to go back to this drawing. This right here is period 1. And it is a horizontal row. I know that's redundant when I say horizontal row, but I'm going to say it anyway. So period 1 has 2 elements in it, hydrogen and helium. Period 2 starts with lithium. And then you got period 3, 4, 5, 6, 7. So periods are rows. They are horizontal. And there are 7 periods in the periodic table. And it turns out that the moat has 2 rows. One of those rows is actually part of period 6, and the other row is part of period 7. So I'm going to show that to you on my small periodic table. I'm going to zoom in on that. And here you can see this says period 6, cesium. Now you'll notice here that it says barium for 56, and then 57 is actually lanthanum, which is right here, lanthanum. This element, I don't like this periodic table so much because this element actually belongs up here. Okay, it's part of the wall, not the moat. And you see this little thick line between lanthanum and cerium? That thick line says that basically lanthanum belongs above and the moat the moat starts at cerium. So can you see how cerium really belongs there next to lanthanum up here, and we open the wall up? So that means that this is part of period 6. And the same thing goes for here, where we have radium and then AC, actinium. Actinium belongs up here. And the next element, this TH, this thorium, that's the beginning of the moat, but it's part of period 7. So is that clear that there are 7 periods? And the top row of the moat is part of period 6, and the bottom part of the moat is part of period 7. Capiche? And that's best explained by this, because here you have 1, 2, 3, 4, 5, 6, 7. And here, part of 6 and part of 7. Okay. Next thing I want to explain to you about the periodic table is this, and this is really important for the rest of chemistry. If you don't memorize this, you're going to be in a world of hurt. Okay, this should be a little taller on this side. This should match up with that, and so forth and so on. There's an element right here. So it's right there, boron. And I'm going to zoom out so you can see my horrible periodic table, and I'm going to trash it. And I'm going to trash it so I can draw a beautiful periodic table. So here's a 1, 2, 3, 4, 5, 6, 7. And right here at the bottom of 3 is where you draw the wall. So there's actually 1, 2, 3. 1, 2, 3 before you get to the wall. The other tower goes up by 2, goes across 5, and then you have this little lookout, if you will. And here's your moat. And this is part of 6, and this is part of 7. So we just discussed that, and we know that this is 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. And the element right here is boron. And then down one row, we have silicon, and down another one, we have arsenic. And then we have tellurium, and then we have astatine. So 4A, 5A, 6A, 7A. And then here we have OG, which is part of 8A. Now, this is not what your book tells you, but it's what I'm going to tell you. These elements here are called metalloids. Your book will actually tell you that it's not quite these, there's a couple more, but we're not going to worry about that because this is easier to figure out. Find boron, draw a diagonal. Those elements on the diagonal are the metalloids. Any questions there? These guys over here are the nonmetals. Now, this element right here, hydrogen, is also a nonmetal. So you want to know that too. And then the rest of these are metals. And if we take a look at some of the elements in the metals like copper, zinc, gold, silver, those are obviously metals, but you know, surprise, surprise, sodium's a metal, potassium's a metal, magnesium's a metal. Well, that makes sense. But there are things in there that are metals where you might not expect them to be metals. Okay, so you want to memorize that. And the reason you want to memorize that is because when you get to formulas of compounds, knowing the difference between a nonmetal, a metal, and a metalloid is going to be hugely important. Now I'm going to go one step further, and I want to give you properties of metals, metalloids, and nonmetals. Properties.
So Tony, at the very beginning of the book, it doesn't have astatine and the OG. I can't pronounce that. It doesn't have those last two that you drew as metalloid.
Right, and I explained that. I explained that the book is different than me, but the reason we go with what I'm doing is because it's easier. Okay.
Okay. I'll try and memorize what's easier. Got it.
Yeah. So what's the purpose really of the metalloids? Take a look. What is the purpose of knowing where that line is?
Separation.
It separates the metalloids or the metals from the nonmetals. That's why you want to know it. So the details don't matter because those elements that you talked about, you know how often we run into those in a general chemistry class?
Probably never.
Never. So what? Who cares? Just remember it's the diagonal to the right, nonmetals, but with hydrogen. And to the left, they're all metals.
Okay.
Easy peasy. This class is tough enough with it as it is.
Yes,
All
sir.
right. So let's look at properties of each of these. And, you know, it's common for me to, on an exam, make a question that says, give me properties of metals, metalloids, and nonmetals. So let's make some lists of these things. Metals, solid at room temp. What does RT mean? Room temp.
Room temp.
They're all solids at room temp, except for one. It's called mercury. It's a liquid at room temp. So when you have like, you know, 80 of these and they're 79 are solid at room temp and one's a liquid at room temp, you say, hey, they're solid at room temp. Nonmetals, most are a gas at room temp. But there is one liquid at room temp and the rest are solids. Metals. You'll notice I'm skipping metalloids. Metals, they are malleable and ductile. Malleable essentially means that when you hit them with the hammer, they don't shatter, they bend. In fact, that's how they used to make coins. You would take a plug of silver that weighed a certain amount, and what you would do is you would put it down on a rock, or actually you put it down on something that had like a face on that rock, and then you'd hit it with a hammer that had a face on the hammer, so that when you hit it, you put the face on the coin from the front and the back. And that's why ancient Roman coins are rarely centered, because to hit that plug with your hammer just right is nearly impossible. But that's the better job when you're making coins, is the person who holds the hammer. You don't want to be the person who holds the coin. They didn't last very long. That's kind of funny, right? All right. So they're malleable and ductile. Nonmetals, if they're solid, because we're talking about solids here, if they're a solid, they're brittle. So what happens if you strike them with a hammer? Something that's brittle.
Shatter.
Shatter. That's exactly what I'm looking for. These conduct electricity. And they conduct heat well. So we'll call that one thing, just like this is one thing. These guys, they're non-conductive. What else can we say about these? These guys have high melting points and boiling points. So what's MP stand for?
Melting point.
Good. And BP?
Boiling point.
Right. And these are low melting points and boiling points. So this is a 1, 2, 3, 4. For the most part, metals are not soluble in water. So not water soluble. And nonmetals are not water soluble. So if you have something that you want to figure out if it's a metal or a nonmetal, and you throw it into water and it doesn't dissolve, Are you going to be able to tell the difference? No. But some of these characters I'm giving you aren't about differences. They're just a character of the material. Okay, so metalloids. What does metalloid mean? It means like a metal, similar to a metal, but not precisely. Most of your metalloids are solid at room temp. Most of your metalloids, well, some of them are kind of brittle or malleable. Do they conduct? Well, a perfect example of a metalloid is silicon. Silicon does conduct, but not very well. So what do you call something that kind of conducts, but not very well?
Semi.
Semiconductor. So here, silicon is a semiconductor, but we would write that some conduct well, others poorly. So that's kind of like a metal, but not. What about the boiling points and the melting points? Well, they're low to high melting point, boiling point. What about the solubility? They tend to be not soluble in water. And we might add to this list later, but these are the ideas. And each metalloid has its own set of properties. They're not all exactly the same. For instance, silicon is a solid at room temp. It's brittle. It conducts kind of. It has a high boiling point and melting point, and it's not water soluble. Okay. But that would change for other metalloids. So you want to know these properties. Fair enough? And now we can actually answer this question. So we want to give the symbol, atomic number, group number, and period, and describe it as a metal, metalloid, or non-metal. So those that begin with an S, so we have Si. Its atomic number is 14. So remember, the symbol for atomic number is Z. Even though it should be an A, it's a Z. So silicon, the atomic number is 14. The group number is 4A. The period is 1, 2, 3. Any questions about silicon? Described as a metal, metalloid, or non-metal. What are we going to say for silicon? Is it part of the diagonal?
Yes.
Metalloid. Okay, can you see selenium here? Oh, we're also supposed to name them. So a lot of people make the mistake of, for silicon, saying silicone. It's silicon. Silicon. Silicone is the stuff that you caulk your tubs with. You with me? Okay, this is selenium. I'm going to put that over here. The atomic number is 34. The group is 5A, no, 6A. It's in period 1, 2, 3, 4. And it is according to Tony, a non-metal. Now I'm going to be honest with you, the closer it is to the metalloids, the more likely it is more like a metalloid. That's just the way it is. Proximity matters. Okay, if we continue, can you see SB? That's antimony. And according to Tony, it is a metal because it's to the left of the diagonal. You can actually see the darkened diagonal line here, and antimony is to the left of that. Antimony is in group 5A. And it's in period 1, 2, 3, 4, 5. And the atomic number for antimony looks like it is 51. And if we look, we'll find out that there are no others. Any questions about that? Okay, that being done, let's go ahead and move on.
Wait a minute.
Yeah?
Tony,
Yes,
that asks for all the S symbols between 4A and 6A, and you're
Yeah.
skipping sulfur and tin, which are both.
oh,
Okay.
thank you. So sulfur and tin. So I'll let you actually fill those out. How does that sound? Give you a little bit of practice. We
Got
did
it.
3 out of 5. Okay. So rather than just copying, you're going to actively look for these.
Done.
Okay, let's move on. Let's see now. I got to make sure that I'm not losing my pages here. And I'm starting to. So this goes over here. How many elements occur in the 7th period? What is the name given to the majority of these elements, and what well-known property characterizes them? Okay, so let's take a look. Here is your periodic table. I'm going to zoom in on it just a little so that we can count the elements in the 7th period. Okay, so can you see all the elements in the 7th period? We're going to start here. 1, 2, 3. Actinium is counted. Then it goes down to thorium. So 1, 2, 3. And then if we go from thorium to lawrencium, that's going to be 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 14. Okay. So we've got 3 plus 14 is 17, 18, 19, 20, blah, blah, blah. And then another 6 here. Now, the way I actually count them is this. Can you see that there are 2 in the left tower? Can you see that there's 1, 2, 3, 4, 5, 6 in the right tower? And there's 10 in the wall, and there's 14 in the moat. So 2 plus 6 is 8. 8 plus 10 is 18. 18 plus the 14 below is 32. So how many elements in the 7th period?
32.
32. We've got 2 here, 10 here, 6 here, and in the very bottom, you got 14 here. And that adds up to,
You're zoomed way in.
oh, thank you. Don't want to do that. So now you can probably see we've got 2 here in the tower, 10 in the wall, 6 in the tower, 14 in the moat. Add that all up together and you get 32 elements. Now, what is the name given to the majority of these elements? About the only elements that are different are this one here, OG, which is a metalloid, according to Tony. But what are all of these to the left of the OG?
Metals.
Metals. So what is the name given to the majority of these elements? Metals. What are the well-known properties of metals? Solid at room temp, high melting point, boiling point. They're malleable. They conduct electricity. They conduct heat. They're not water soluble. Boom, boom, boom. Capiche?
Yep.
Okay, so let's move on. Give the name and chemical symbol for the following. A non-metal in the 2nd period. Name and symbol. So do you see lithium here? Is that a non-metal in the second period?
No.
No, it's a metal in the second period. Oops, I got to go past boron. So for A, we could do carbon, nitrogen, oxygen, fluorine, or neon. I'm not going to write the names out for you except for one of them. I'm going to write the name of only one of these. And I'm going to write it out twice. Which is the correct spelling? The one above or the one below?
The one above.
The one above, because the one below says fluorine. There is no element called fluorine. Okay, non-metal in the second period. B, alkaline metal in the fifth period. So we're learning more about the periodic table. So I'm going to give you a little bit more about the periodic table so that you can answer these questions. So I'm going to draw these again, just quickly. And I'm going to do 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. And you want to know these about 1A. They're called the alkali, and most of them are metals except for hydrogen. 2A, they're called the alkaline earth metals. And they're named so similarly that I have to invent a stupid reason to try and remember it. So they're both metals, the 1As and the 2As, but the way I kind of remember it is that if you get rid of the metal part, group 1A only has one part to the name, alkali. 2A has two parts to the name, alkaline earth. But not only that, because this one is the second group and not the first group, like the second born, it's got a little chip on its shoulder. So alkali isn't good enough. It has to be alkaline, a little extra. You know how those second born children are, always a chip on their shoulder. I'm a second born, but I was mom's favorite. And you might think, God, he's got a big head. And actually, my mother is a traditional Japanese woman. And I was the only son in my family. So if you know anything about Japanese women and their son, I was the favorite. I didn't have to do anything. I was just born a male and I was the favorite. And I don't apologize for it. I tell my sisters all the time, I was mom's favorite. And you know why. Okay. So, I'm sorry. 7A, you want to memorize as the halogens. And 8A, you want to memorize as the noble gases. But sometimes they're called the inert gases. And sometimes they're called the rare gases. Now, they're called rare gases because they're rare. They're called inert gases because they don't react. They're unreactive. They're called noble gases because when you look at the noble versus the peasants, so inert gases, they don't react. That means they don't react with other elements. Do the noble react with the peasants? Nope. Which are rare, the noble, nobility, or the peasants? The nobility. So that's why you call them noble gases, because that kind of captures that they're above it all and they're rare. Any questions about the noble gases? This is the most common term used for them, noble gases. All right, so now we can answer B, an alkali metal in the fifth period. So that's going to be group 1A. We go down 5 elements and we find rubidium. And here a third period halogen, you can find that now. An element that is a gas at 20 degrees Celsius and at 1 atmosphere pressure. So let me show you on the periodic table the gases, okay? All of these are gases. of course, because they're noble gases at room temp. Fluorine and chlorine are gases at room temp. Oxygen and nitrogen are gases at room temp. And those are the gases: nitrogen, oxygen, fluorine, chlorine, and hydrogen. So those are the gases at room temp. The liquids at room temp are mercury and bromine. And I'm going to put Br2 because it's a Hunkelbrief. So when we look at the periodic table, what is the state of these at room temp? Most of them. If they're not a gas and they're not a liquid, what are they?
Solid.
Solid.
Solid. So there's only 2 that are liquid at room temp. There's about maybe 10 of them that are gases at room temp, and the majority of them are a solid at room temp. So when you're trying to memorize these, what's easier to remember? The 100 of them that are solids, or just remember the 2 liquids and the 10 gases, and then the rest are solid? The answer is memorize the 2 liquids, the 10 gases, and the rest are solid. So memorize the 12 and then go on from there. Fair enough? So an element that is a gas at 20 degrees Celsius and 1 atmosphere of pressure, I'm going to choose a noble gas because I have, 5 or 6 different elements to choose from. Fair enough? Okay. Here are symbols for 5 of the 7 elements whose name begin with the letter B. Match each symbol with one of the descriptions below. So, a radioactive element. It turns out that when you look at the periodic table, some of these elements are radioactive. Now, do you see this one here, PO? PO stands for polonium. It is named after the country Poland. It was discovered by Marie Curie, a famous scientist who studied radioactivity. And she actually died due to radioactivity poisoning. Every element from 84 on is radioactive. Every element from 84 on is radioactive. Now, what about the elements before 84? Some of them have radioactive isotopes, and some of them don't. So the only thing we can guarantee is that every atom beyond from 84 and on is radioactive. Okay. So we're going to leave it at that for the moment. Now, if you look at this periodic table, you see the parentheses here, like technetium 98. That usually indicates that this only has a radioactive isotope. And you see those from 84 on, they're all in parentheses. On this periodic table, that indicates radioactivity. Okay. Now, some of these should have parentheses around them, but they don't, like uranium, definitely radioactive. Okay. Match each with its symbol. So a radioactive element, let's see, I'm going to look for something like BK, berkelium. Why? Because it's 97, which is greater than 84. So radioactive element, berkelium. Berkelium or something like that. I'm never sure how to pronounce that, but it's named after Berkeley because they discovered that element at Berkeley. Turns out that in science, if you discover an element, you get to name it. So, if you wanted to, you can name it Fred Flintstonian. Okay, a liquid at room temperature. Well, we learned that bromine is a liquid at room temperature. A metalloid, that would be boron, because that's the beginning of the diagonal. An alkaline earth metal, that would be barium. And a group 5 element, that must be whatever remains, which is going to be bismuth. Any questions there? So what did we really learn here? We learned that everything from polonium on is radioactive. That's what we really learned. Capiche? Okay. A model of the amino acid asparagine is illustrated here. Write the molecular formula for the compound and draw its structural formula. So I'm going to have to teach you about structural formulas. And it's probably not best to do it with asparagine, but let's go ahead and look at asparagine in our book. So page 108. So here's asparagine. Now, the gray spheres, I'm looking for my remote here so I can zoom in. Okay, there we go. Zoom out just a little bit and rotate my camera. And we can see asparagine. The dark spheres that are kind of grayish black, those are carbon atoms. The blue ones are nitrogen atoms. The red ones are oxygen, and the white ones are hydrogen. And this is the way all of these work. Anytime you see these dark ones, they're carbon, period. Blue ones, nitrogen. Red ones, oxygen. White ones are hydrogen. So to draw the structural formula of this thing, we want to take those little spheres and replace them with the letter of the element. So that's what a structural formula is. It's just the atoms represented as symbols and bonds represented as lines. So does everyone see right here what I'm pointing at? There's a line between the red sphere and the black sphere. That's a bond. Now down here, do you see that there's two parallel lines between that black sphere and a different red sphere? That's a double bond. What would three parallel lines be called?
Triple bond.
Triple bond. And what would happen if you had between this black sphere and this red sphere, James? What would that be?
What?
A
James?
James Bond.
Yes, James Bond. Okay, so let's actually, what I'm going to do here is I'm going to show you the answer here while we're looking at it in the book. It's a little difficult for me to do, but we're going to manage it. I have to put something underneath my book to prop up the page. I'm going to back it out just a little. And so let's draw this structure on this card here. Now I'm going to start right here with that little red sphere. That's an oxygen. And then it goes to a carbon and then a double bond to an oxygen. So do we all understand what I've drawn here compared to here?
Yes.
Yes.
Okay, now do you see there's a single bond that goes to a carbon here? And you see that carbon has a bond that goes to a white sphere. So that's going to be a hydrogen. And then another bond that goes to a blue sphere, which is a nitrogen.
Can you zoom out just a little bit?
Yep, I see I've run into the limits. So do you see how this sphere here is bonded to a hydrogen and bonded to a blue atom, which is a nitrogen? Are we good? Now, we're not trying to duplicate the dimensionality of this thing. We're just trying to show how everything's connected. Do you see how there's three hydrogens bonded to that blue sphere here? So three hydrogens. Are we good?
Yes.
So I'm going to draw a line going down. What atom is there? Carbon. 2 hydrogens. Line going up to a carbon, and that is a double bond to an oxygen. Single line to a nitrogen, and then a hydrogen and a hydrogen. So this is the structural formula. Now, do you see the watermark behind this molecule? Where you see this kind of reddish black. This watermark is called the space filling model, and you don't see the bonds. You do not see the bonds. So in this space filling model, what is a bond? It's where 2 atoms meet. There's a bond there. But you can't tell if it's a double or a single. And this thing that we're looking at here, they actually call this the ball and stick model. The atoms are balls, and the bonds are sticks, ball and stick. And what is this one called? The structural formula. Where we show the atoms as symbols and the bonds as lines. Okay, any questions about that one? So that's asparagine, and we just drew its structural formula. I'm going to back out of this now. And so that was our answer for that based on what was drawn in the book. Any questions, people? Okay, we're going to move on. Okay. Now this part, what is the charge on the common monatomic ions of the following elements? This is something I'm going to reserve for tomorrow because this deals with naming compounds. And we should know the charge on each of these, but we'll be covering that tomorrow in lab. And so here, 38, that's a lab question. 39, that's a lab, or 40, that's a lab. 42, another lab for tomorrow. 44, lab tomorrow. 46, lab tomorrow. 48, lab tomorrow. 50, lab tomorrow. 52, lab tomorrow. 54, lab tomorrow. 56, lab tomorrow. 58, lab tomorrow. 60, lab tomorrow. And then we're on to material that's not going to be covered in the lab tomorrow. So if you want to do those problems, you definitely want to show up for lab tomorrow because we're going to talk about how to name compounds and how to get the formula of compounds. So in other words, if given the name, how do you get the formula? If given the formula, how do you get the name? So let's move on to number 62, which is calculate the mass in grams of each of the following. So here's what we want to learn about the periodic table so that we can do this very efficiently. So this is the symbol for carbon. This is the atomic number, which is equal to the number of protons. This is the symbol. And this is the atomic weight. So this is the average mass based on the isotopes. So carbon has an isotope that's like carbon 12, there's a carbon 13, and there's a carbon 14. So carbon basically has 3 isotopes, and carbon 14 is radioactive. You don't need to know that, but take a look at these three isotopes. How much does that one weigh? 12.0 AMU. How much does that one weigh? 13.0 AMU. How much does that one weigh? 14.0 AMU. So which of these isotopes is more abundant, meaning a larger percentage of the carbon atoms? Carbon 12, carbon 13, or carbon 14, based on the atomic weight?
12.
Yeah, it's
12.
mostly carbon 12. It's like 99% carbon 12. Fair enough? Okay. Now, there's something else that we need to learn. It's something called a mole. So there's this thing called Avogadro's number. And we want to actually calculate it. Let's suppose we have 12.01 grams of carbon. I want to find out how many carbon atoms that is. Okay, are you with me here? Here's what I'm going to do. I'm going to take my 12.01 grams of carbon. I'm going to turn that into atomic mass units of carbon, and then I'm going to turn that into carbon atoms. So for my first conversion, I'm going to use this, that 1 AMU is equal to 1.66054 times 10 to the minus 24 grams. So that's how I'm going to convert between grams of carbon and atomic mass units of carbon. Secondly, when I look at the periodic table and I see that carbon has a 12.01 at the bottom, I know that one carbon atom is equal to 12.01 AMU. Or I'm going to put a U there to be consistent with that and that. So here's my first conversion. Here's my second conversion. So I'm going to take my 12.01 grams of carbon and multiply by this first conversion, and then multiply by this second conversion. And when you're done with this problem, give me a little thumbs up and we'll take a look at your answers compared to mine. And we're going to use 12.011 here. We're going to start with 12.011, and that's the 12.011 there. So I'm going to put that on the bottom, and that on the top. Should have a C there. Okay, you get an answer? Okay, so we get 5 significant figures, 6.0221 times 10 to the 23 carbon atoms. So this is interesting. You'll notice that this number matches the atomic weight of carbon, but instead of atomic mass units, I said, okay, that's how many grams I have. Now, if we take a look at oxygen, 15.9994, and 8 goes at the top, how much does one oxygen atom weigh? Well, one oxygen atom weighs 15.9994 atomic mass units. How many oxygen atoms would weigh 15.994 grams without doing any calculations? Well, let's think about this. Do you see that 12 grams of carbon is this many atoms? What would 12 grams of oxygen be as far as atoms go? And the answer is it'd be less than that because oxygen atoms weigh more. It's kind of like saying if you have 12 grams of eggs, you can have a certain number of eggs. But if you have 12 grams of potatoes, you're going to have fewer potatoes because potatoes weigh more. Okay. Now here,
Tony,
yeah.
I'm sorry. I'm looking at your calculation there and that answer, and I don't understand how you got that answer, but maybe I've done something wrong. Because
Well-
doesn't the 12 point, why is it a 6 when you're canceling?
Because
I guess
12.011 cancels 12.011.
Right?
So you have 1 divided
Yeah.
by 1.66 times 10 to the minus 24.
Yes.
Okay, so let's estimate the answer. 1 over 1.66 times 10 to the minus 24. How many times does 1.6 go into 1? Roughly 0.6 times. Does that make
Okay.
sense?
Yeah.
Now the 10 to the
Yes,
minus
thank
24
you.
becomes 10 to the positive 24. And then when you fix this up, it becomes 6 times 10
Thank
to
you.
23.
Okay.
Okay, so back to this. I want you to think about this. If I have 12, I'm rounding. If I have 12 grams of carbon, I have that many atoms of carbon. So if I go to oxygen and I want that many atoms of oxygen, since each oxygen weighs more than carbon, the mass of oxygen must be a little greater. So the answer here is 6.022 times 10 to the 23. Same number as that. So here, for any element, the number at top is the atomic number, but the number at the bottom means 2 things. It means that 1 carbon atom is 12.011 U, but also means that 6.022 times 10 to the 23rd carbon atoms is 12.011 grams. So that number at the bottom means 2 things. That many atoms is that many grams. And that 1 carbon atom weighs that many atomic mass units. Now, this is a value we use in chemistry so much that we give it a name. For instance, have you guys ever heard of a dozen?
Yeah.
A dozen is 12, right?
Of course.
And a baker's
Yeah.
dozen is, what's a
13.
baker's dozen? 13. So those
13.
have definitions. This number has a definition in chemistry. It's called a mole. It's also called Avogadro's number. So that's why we started this with Avogadro's number. So let's recap what you just learned. And this is something you need to memorize. So I'm not going to write carbon here. I'm going to write a different element down. I'm going to write gold down. So gold is like 97 or something like that. Nope, 79, not 97. It's 196.9666. So let's write down the information we can get from this. Number one, the number of protons is equal to 79. Number two, one gold atom has a mass of 196.9666 U. Thirdly, 1 mole of gold atoms, which we write down as 1 mole of gold, these mean the same thing, is equal to 196.6 or 9666 grams. And another thing we could say is that the symbol of gold is AU. I mean, if we want to get down to the nitty-gritties there. So let's use this idea to tackle this problem that we're looking at. Number 62, calculate the mass in grams of each of the following. 4.24 moles of gold. I'm going to take this 1 mole of gold and put it on the bottom. And I'm going to take this and put it on the top, only I'm going to add a label. What label should I add to this guy? And the answer is gold, because we're talking about grams of gold.
Oh, gold.
Okay, same label on top and bottom. So 4.24 moles of gold is going to weigh 4 times this, and I'm going to estimate. What's 196 if we round it to a very easy number to work with? It's 200.
197.
200.
Oh,
No, 197.
okay.
What's 4 times 197?
Super easy. Right.
Do that.
Sorry.
I'm going to go with
Sorry.
200. Let's make 4.24 something easy to work with.
Okay.
How about that? How about 4?
2.4.
4 and 200. What's 4 times 200?
800.
800. Now, is it clear that the answer should probably be a little bigger than 800?
Yeah.
So we just estimated. And if your calculator spits out 8,262, you messed up. How many significant figures are we allowed?
3.
3. And I get 835 grams of gold. And this is the work I would expect to see for letter A. You don't have to show me all of this stuff. This comes right off the periodic table.
Tony,
Yes.
what periodic table are you using with that measure of specificity for the
The book.
196?
The book. Now,
Um,
turns out if you used 197.0, let's see what our answer would be, okay? So what's our answer if we use 197.0?
Um, 835.28 with 3 significant figures comes out to 835.
So it comes out to the same answer. It turns out that when you're converting something into something else, for this value here, you want 1 more significant figure than what you have over here. The rest really doesn't matter. So we could have used 197 and been just fine. Okay. All right. So let's do this one, B. 1 mole of helium. So I'm going to write the symbol helium on my paper here. And I'm going to pick the number off the book, and I'm going to write one more significant figure than what we have here. So 4.003, one more significant figure than there. So how do we set up B? 15.6 mole of helium. Do you notice how they don't put an E on the end of mole? The reason they don't do that is because the abbreviation for mole, M-O-L-E, is M-O-L. That's an abbreviation. I hate that abbreviation because when I see that, I think molecule. So I don't abbreviate mole. You're only saving one letter. What's the point? Okay, now what am I going to multiply by? I'm going to put 1 mole of helium on the bottom, and how many grams on top?
4.0026.
I rounded that off, but yeah, 2.6 would be fine. And if you did this with 2.6 or with 3, you're going to get the same answer. Let's see what we get. Let's estimate. What's 4 times 15?
60.
60. So the answer should be 60-ish. Clearly a little bit more because that's not 15, it's closer to 16. So maybe 64-ish or 63-ish, something like that. How many zig figs are we allowed?
3.
And I get 62.4. So this concept here, 1 mole is equal to 4.003 grams. This is called molar mass. The mass of 1 mole of a substance. And I really like this name molar mass because we're talking about, oh, and I should say the mass, comma, in grams, comma, of 1 mole of a substance. That's the definition of molar mass, the mass in grams of 1 mole of a substance. And you need to remember this, that 1 mole is 6.022 times 10 to the 23rd. This only has 4 significant figures. We know it to a lot more significant figures, but I want you to memorize this, just the 4 zig figs. So any questions about how to do B? So how are you going to do C? Here's what I'm expecting for an answer. You're going to say the same, only we're going to use the molar mass of platinum. So how are you going to do C?
Same, except for platinum.
Okay, how are you going to do D?
The same, except for plutonium.
Plutonium,
Pu.
correct.
Okay.
Named after Pluto, which of course was named after probably some Greek god.
D.
Okay, how are we going to do? We're going to do one of these problems and then end it here. How would we do number 16 or number 64A? Well, we would have 16.0 grams of sodium, but in this case, we'd multiply by 1 mole of sodium over 22.99 grams of sodium. So do you see here? I'm putting the mole on top and the grams on the bottom, but that's still the molar mass. So why did I put the grams on the bottom? So things will cancel. And if we estimate this answer, is it easy to see that the answer should be a little bit smaller than 1, but maybe a little bit bigger than half?
Yeah.
So I get 0.696 mole of sodium. Does that answer make sense given the two numbers we began with?
Yes.
I think it does. So how do you do B?
The same except for with SN 10.
Right. How do you do C? The same except for the molar mass of platinum. How do you do D? The same except for the molar mass of xenon. Okay, so we've done some good work today. We will hopefully see you tomorrow for how to name compounds. All righty. Thanks for
Thanks
attending.
for your time.
Bye-bye.
Thank you. Bye.
Bye.